Okay, so hello everybody. Welcome to our last colloquium before Christmas. So, of course, to everybody, happy holidays and hopefully to a great 2013. And as a special treat, we have today Hans-Walter Rix, who is, of course, one of the directors of the MPIA, and recently just got one of the big ERC grants and has way too much stuff on his CV than for me to talk about in 45 minutes. So without further ado, I'll just give you Hans-Walter and his Christmas story about how the Milky Way disk started.
Okay. Yeah, good afternoon. I'm happy to try to do the year closing colloquium. And as many of you know, for the entire 13 years that I've been in Heidelberg, I've been interested in the Milky Way in the local group. Some of you had to sit through talks that I gave on destruction, substruction, the outer stellar halo, because that is such a perfect diagnostic of the merging prehistory of the Milky Way, and that's true. Or talks about the ultra-faint galaxies and their abundances, because that is the best way to study how galaxy formation becomes asymptotically inefficient in low dark matter halos. That's also true. But then about 2 years ago, I had a somewhat embarrassing epiphany about the Milky Way, which is particularly embarrassing if you look at this picture, because after working for many years, I've been mostly interested in all the nothings out there, it became clear to me that, goodness, most stars in the Milky Way are actually in its disk. And it's interesting, my only excuse for having had this epiphany so late is indeed the community as a whole actually if you look at it, I would bet that over the last 10 years, the number of good and widely cited, etc., papers on the Milky Way that deal with the little stuff at the outside, there are 5 times more than good papers on the disk. So, but let me now tell you what I've enjoyed working on and doing on the disk over the last 2 years, and I should acknowledge my 2 main collaborators in this, Joe Bovey, who is a regular summer visitor here at the Institute and now a Hubble Fellow in Princeton, and Greg Stinson, who is in Andrea Macho's group at our Institute. So what makes the Milky Way's disk interesting? Because while it's always said, and I'll show you in practice what it means, that we can study it in unprecedented detail, the question is, how useful are those results in a broader context? And so one of the good things is that our own Milky Way is in many ways a horrendously average galaxy. About half the stars in the present-day universe live in bigger galaxies, half the stars live in lower mass galaxies, half live in more metal-rich, half more metal-poor, bigger, etc. So we are the average galaxy in the universe. Luckily, we're somewhat unusual in 2 respects. The first respect is for a galaxy of 5 or 6 times 10 to 10 solar masses and stars. We are surprisingly disk-dominated. And secondly, for a galaxy with that many stars, we seem to have a slightly anemic halo, which perhaps one should look at the other way around. From our halo, the Milky Way was particularly efficient, perhaps by a factor of 2 more than average in making stars. But that aside, we are average. And we look at the disk because this is where most of the stars are. I guess an interesting the reason is because, indeed, making from ab initio simulations realistic-looking disks is still formidable. There are now defensible claims that that can be done. But I'll show you that how well those simulations resemble the Milky Way's disk depends on how hard or in which way you look. Finally, of course, the alternative to studying galaxy evolution by archaeology is to do looking back in redshift. But if you ask how easy is it to actually do the kinematics not of gas, but actually of stellar disks at high redshift until JWST comes, which is now, as always, 6 years from now, as it's always been for the last 15 years, is still hard. So it's hard to use high redshift observations of the stellar kinematics, at least, to figure out the structure of the disk. And as I'll show you with some examples, the Milky Way allows perhaps some of the most direct tests of asking what sets the structure of the stellar disk. Now, structure means what sets the size, what sets its radial profile, what sets its vertical profile. Now, for all of these things are conventional truths out there. The size of a disk is given by, angular momentum arguments. And in a disk, of course, if there are no mergers, there's no particular reason that angular momentum should change drastically. So the disk structure radially might perhaps reflect the initial angular momentum structure. One of the interesting wrenches that has been put in there, it goes by the term radial migration. That even if you have a disk that it does not experience any mergers, nothing traumatic, but has spiral arms and bars, some mild non-axisymmetric features, it turns out that resonance scattering, near co-rotation, and other things, lead to quite dramatic changes of angular momentum. This is from nice plot from Ivan Minchev in simulations. What's shown here is the change that a star experiences, a disk star, in its angular momentum by interacting with bars and spiral arms versus its initial angular momentum. Initial angular momentum typically is in these units 5 and changing by of order unities that much. And this is how much angular momentum changes after 1 dynamical period, 5 dynamical periods, etc. So it is quite plausible that even in an environment as benign as our Milky Way, stars get randomized in the radial direction by a lot. That's true for individual stars, but mostly they just trade places. That's actually an idea that, like many disk ideas, was tossed around, I guess also by Whelan, probably 30 or 40 years ago, who was musing about why the sun was slightly more metal-rich than the average here, and perhaps it came from the inside. That's something I'll come back to. But perhaps more, what sets the vertical structure? Well, you all have learned gas settles into a thin disk. Stars are born in a thin disk, and then either impulsively by infalling satellites they get heated, or successively by scattering off molecular clouds, etc. And then the thickness or the vertical temperature of the disk just reflects how much the stars have been heated over time. And another question that we'll look at is whether distinct thin and thick disk components are a sensible description, because the traditional picture for making a thick disk is our Milky Way was busy assembling itself a nice thin disk. Somewhere at redshift 1.5, a fairly big bad satellite came by, shook up the disk quite dramatically, created a thick disk, after which the Milky Way then said, okay, we have to rebuild after this earthquake, and built itself a new thin disk. So that's... Now, what I want to do is look at some of this in light of present-day simulations, just to set the stage now, and then actually show you to which extent the Milky Way chooses to actually conform to the conventional wisdom about itself, and what in the end we can say about some of these aspects of the mechanisms that set the structure of the disk. What I'm now going to show you is, to set the stage, 2 different simulations, one from Marie Martig. Both are geared with different techniques, the other one from Greg Stinson, to do something, end up with something that is vaguely Milky Way-ish. This is a simulation that actually starts quite well after Big Bang. There's gas and dust on the left side, stars on the right-hand side. And let's see, hopefully the thing will run. And what I want to use that simulation for is just to say that, even if you pick a fairly quiescent merging history, something always happens. There is some irritating satellite coming in. Mostly here you see stars. And then for a while you have a big bar. You always have spiral arms, always these non-axisymmetric features that can stir the disk. So you also saw, and you'll see this in the next simulation, the other generic feature is that the stars that form earliest form in the middle. So you have inside-out growth. So many things happen all the time, and you have inside-out growth. This is a simulation from the MAGIC project that Greg Stinson and collaborators ran. Here, its claim to fame is that Greg and collaborators included what you see here, I should say, in green, is you see here more the gas coming in directly, and the blue and red things are the stars as they form. Here you also see the crucial ingredient in all of this, namely feedback to the gas. Occasionally you see getting directly heated. It turns out that Greg and now also others say the only way to get a disk-dominated galaxy, which means to prevent too much star formation that makes a very dense lump in the middle, is not only to use supernovae as a mechanism to bring energy back into the interstellar medium, but also acknowledge that young stars, by winds and radiation, even if they don't, and even before they go supernova, put back. Now, by the way, we're now approaching redshift 1, if you have your cosmology at the tip of your hand, and you see that after a very wild and early phase, now a stellar disk is emerging and more gas is coming in to build up the disk. Now, movies are fine, but not quantitative and do not lend themselves immediately to a comparison with observations. So what, in a recent paper, Greg, Joe Bovey, and I have done is take that simulation and try to bring it a little bit more towards the plane of observables. And now imagine you could just say, let me just look at all the stars in the Milky Way that were born between 9 and 10 gigayears ago, 8 and 9 gigayears ago. That is, you make coeval populations, ask where they were born and where they are now. In some sense, that's what encodes the formation history of the Milky Way. And if you do that, I'll show you here sets of panels that are 20 kiloparsecs on a side. The sun's location is here. This is the location of stars at birth that were born more than 10 gigayears ago. Galactic center is here, the sun is here, and where they are now. You actually see, because of dynamical friction, they got slightly more concentrated. Now I'll walk you through younger populations. Now, those stars were already born kind of in a disk-like configuration, but a really fat disk that looks somewhat similar nowadays, even just a little bigger. But it turns out, right, unsurprisingly, that most of the really old stars are in the middle, and we sit at the place where only few very old stars get. Let's go down towards younger epochs. And notice here it's a distinct disk, but still quite fluffy, that gets heated subsequently a little bit, or at least it ends up thicker. Now is it still going down? Yep. So what to translate this comparison in the movie into something quantitative, if you then say, fine, let me just pick all the stars of a given age and assign to them a radial scale length and a vertical thickness measured at the solar radius. Vertical thickness is here, and radial scale length here, and that is old. Yeah. So the simulations clearly imply that the oldest stars are a thick and centrally concentrated configuration, and then galaxy formation proceeds towards stars forming in more extended and thinner configurations subsequently, each of which, after birth, get heated at least somewhat. So, cast in words, you have inside-out growth, but you also have a continuum of disk thicknesses, which is well predicted by age. Another, for the thin disk, that's another result that goes back to Whelan decades ago. And the present-day thickness of these, if you pick all the stars that are 7 gigayears old, a good portion of their thickness is the thickness they had at birth, in part because at early epochs, gas did not need to settle into a perfectly thin disk before it formed stars. And you have also an outward metallicity gradient, which I did not show. So if you're a galaxy formation person, that makes all perfect sense, and how could it be otherwise? Things settle down, and high angular momentum material comes in late. But that certainly flies into the face of two conventional wisdoms. First of all, that in the Milky Way, but also in other galaxies, the thick disks are old, not old. Thick disks are old, but everybody finds that thick disks are radially extended, which in this seems to be a contradiction. And secondly, certainly has been conventional wisdom that the Milky Way has both a chemically but a kinematically and structurally distinct thick disk. So the question is, to which extent the Milky Way follows this qualitative picture of the formations or not? And so to look at that, what we did was ask, what is the best way to actually look at the Milky Way's disk? It's clearly complex, and if you ask, what can you observe about the Milky Way's disk? Well, for each star, you can measure its 3D position, velocity, age, and various abundances, or in some sense, metallicity, the degree of enrichment and alpha enhancement, which reflects the ratio of fast core collapse supernova enrichment to slower type 1a enrichment. So this reflects speed of enrichment, and this degree of enrichment is a somewhat simplified version of abundance space. But you can show, even if you measure 20 abundances, that in a principal component sense, this captures 90 to 95% of what there is to be said about the abundances of a generic star. Now, these coordinates are stupid because radius and velocity vary all the time, and you don't care about this. That's well known. And clearly, the better way to look at things is to look at the orbit of the star as a function of, and then age, metallicity, and alpha enhancement. And that was the original science case. For Gaia, we'll get great phase-based coordinates, etc., and then we'll have this information, and we can reconstruct the formation history of the Milky Way. In some sense, both heating and this radial migration business, which are both processes that, at least for individual stars, switch orbits and change orbits, have led to this being a bit naive. And the orbit in practice, right, is described by things like integrals of motion. Now, it's probably better to take this distribution and separate it really into, it seems like a small difference, the things that are lifelong tags, right? clearly the age of a star, its metallicity, and its alpha enhancement others, no matter what you do to the poor star's orbit, they are conserved. And so the right way of looking at this is really, and I've just replaced comma, is look at the orbital distributions at a given set of lifelong tags. Now, what I'll now present you is a simpler version of it, namely the spatial distribution of stars as a function of its abundances and the velocity distribution. That's for two reasons. First, to actually get the orbits, you need a good model for the potential. That's not impossible, but that's an additional complicating step. And the other thing is, at the moment, except for the immediate neighborhood around the sun, we have to wait for Gaia to actually get ages. So what I will use is the speed of chemical enrichment as a chemical age tag. So this is part that I've looked at. So what I'd like to do is now ask, what if you had eyes only for stars of a certain metallicity and alpha enhancement? And if you could interpret these things in terms of age, what would the Milky Way look like? Would it also go from fat and centrally concentrated to successively thinner and more spatially, radially extended disks? And that brings me to the part where actually much of the work is in, because there are all these fabulous surveys, be it RAVE, be it SEGWE, and what do? They give us for stars metallicities, they're reasonably good, alpha enhancements, they're reasonably good, and to the extent that we know they're main sequence stars, they give us photometric distances, they're good. So we have all these numbers, but what we need to do is ask, what would it be if we just looked at stars of a given metallicity? So that's what we want to do. These are all about 40,000, 30,000 stars in SEGWE, their distribution in metallicity and alpha enhancement. In the sense, metal poor is here, and signs of rapid enhancement, which is only plausible if you're an old star, is up this way. So we pick all the stars that lie here, are abundance-wise similar, that have the same lifelong tags, and ask what is their spatial structure. So both the spatial structure we look at and the kinematic structure. So that actually is a hard technical problem. So what you have is a catalog of stars that were observed with SEGWE, and you know kind of the procedure that went into it so that it would end up in the catalog. What you'd like to get is ask, what would have to be the spatial distribution of those stars so that my catalog looks the way that it does, right? So that's, and the reason why this is complicated is because it's as hard a problem as if you do a galaxy survey. It's not obvious to everybody if people talk about 2DF Sloan or Bose galaxy correlations. You do these subtle effects like the baryon acoustic oscillations, etc. You need to be able to trace the chance that a given galaxy with physical properties ended up in your catalog at the 1% level. And it turns out in Milky Way structure you need similar things. But let me just give you a few examples why you need to work through this. So the procedure in SEGWE is simple. For each plate, we target 65 G-dwarfs brighter than 19th magnitude. Fine. But this is Z and R, at low latitudes, there are many more G stars to choose from. So the fraction of G stars that you actually get to target changes by an order of magnitude whether you look that way or that way. Fine, you can calculate this. Then secondly, You need to have good enough signal to noise to get a good alpha enhancement and metallicity and all this kind of stuff. Now, what's shown here is this is G minus R colors. These are G colored curves, and this is from 15th to 19th. Grayscale is what was targeted, and red is what successfully ended up in your catalog. And you see, not surprisingly, as you go to the faint limit, you have more failed catalog entries because you couldn't get a good metallicity abundance, etc., that type of stuff. So you need, and I'll show you that, and it's actually one of the scariest parts about Gaia data analysis later on. If you can't trace at the 1% level of how you ended up with a good entry in your catalog, the Gaia samples might as well be 30 or 100 times smaller. So that is what one has to do. But then what you can do is just say, fine, let me make a model for the spatial distribution of all the stars that have a given metallicity and chemical age. And look at this distribution. And it turns out, and that's the first of messages that I have, is that for any given abundance, we call these monoabundance populations, they are as simple as can be. Simple exponential in the vertical direction, and a simple exponential in the radial direction. And I'll show you also kinematically they're as simple as can be because they're purely isothermal. So by picking subsets of stars in abundance space, similar abundances, their spatial distribution is as simple as you might imagine it. Where it gets interesting is if you now look how these properties vary as a function of abundance. What you see here, what's shown the color coding, is stars of that abundance, that metallicity and alpha enhancement, have a scale height here of 900, here of 450, here of whatever, 300. It corresponds here. So this is just another way of looking at the same phenomenon, the scale height. So each subset of stars with the same abundances has a single scale height and scale length, and that varies systematically. And you should be pleased because old alpha-enhanced stars, clearly, that's just another way of looking at it, are the ones that have the large scale heights. These alpha old components are thick, but now we ask if we pick all the stars that are very strongly alpha-enhanced, rapidly rich, must be old, what is their radial profile as we look at it from the sun? Are they very centrally concentrated as simulations predict, or are they very extended? Now, blue means has a radial scale length of only 1.5 kiloparsecs, while the brown here is 4 parsecs. So clearly, the old components are also compact. And interesting, if you say at a given age, if you interpret this as age, and I'll get back to that, you find that every time the more metal-rich ones at that alpha enhancement have shorter scale length, are more centrally compact, and the metal-poor stuff is more radially extended. So at a given age, you have an outward metallicity drop. Okay, so just to look at this geometrically, we take advantage of having samples of tens of thousands of stars. You cut them down into 100 samples of 100 stars each and ask what is their scale height and radial scale length. And if you do that, you find that, and red means alpha enhanced or chemically old, blue means young, they're either fat and centrally concentrated or more thin and radially extended. Or this is actually approximately drawn to scale what it means to have a low scale height and a long radial scale length. That's an actual isonumber density contour, etc. That is, indeed, if you take that, if you first define subsamples by their chemical age or their abundances, then old is essentially concentrated in fat and goes successively to thinner and more radially extended. Let me do a quick detour here, because, of course, whatever happened here, you see all kinds of scale heights. Whatever happened to the thick disk, I'll show you in a second. If we actually put the density of all of these stars properly weighted together, their total profile looks like this. And you can well fit it with a scale length of about 250 parsecs and 700 parsecs. So that's just another way of saying, yes, it is true that you can approximate a banana by two straight lines, but that does not mean the banana is necessarily only a two-component system. It seems to me that indeed, there are many, many components, each of which has its own scale height and scale length, and there is a continuum of them. But I'll elaborate on that a bit more in just a minute. What I want to intersperse, because that actually turns out in the long run to be important for dynamical modeling. If you now just ask, let me again have only eyes for stars of a certain age and metallicity, what is their velocity dispersion profile? If you do nothing, everybody knows that stars near the plane have low velocity dispersion and stars away from the plane have high velocity dispersion. But if again you pick stars that are metal rich and young, fine. They have a velocity dispersion of only 12 kilometers a second, all the way out to 1.5 kiloparsecs above the disk. If you pick those, they are hot throughout, etc. And of course, if you average over all of them, their relative contribution shift, and you end up with a rising profile. But almost bizarrely, if you pick stars of identical abundances, they self-sort themselves in a sequence of perfectly isothermal subpopulations. And if you ever have tried to model disks and disk components, isothermal is a nice assumption to have, and it's very pretty that it comes out by itself. So, remember I said the simulations disagree in two ways with the conventional wisdom about the Milky Way. The one was that the old population simulations said should be both fat and centrally concentrated, and it seems to be. The other part is the question of a distinct thick disk. And what I want to show you, it's a slight technical detail, but it's actually important, because so far I've only shown you how one fits number density models of G-dwarfs. Right? That's all we've done. The question is, given your selection and given the age distribution, etc., and a plausible IMF, each star that falls into your sample, for how many solar masses of underlying population does it stand? And the reason why that matters is because if you pick stars by color, a low metallicity star, famously a subdwarf or being a bluer thing, of course, has a different mass than a high metallicity star of the same color, and therefore it stands for a different amount of mass in the mass function. And the other part is you need to, the luminosities of metal-poor stars and metal-rich stars are also quite different, and the targeting strategies. So you also need to pull in the effective survey volumes of all of this. So what we did is we just said, first of all, which fraction of a stellar mass is enclosed in this color selection box. You can do that. You can get the densities. And then we also have the scale length, which then allows you to ask how much do stars of a given metallicity and alpha enhancement contribute to the surface mass density at the solar radius. And you see, because of volume effects and all this other stuff, it's what galaxy survey people have done all along, that quite dramatically differs. First of all, this is the sample, what ends up in the catalog, and this is if you do it properly mass weighted, which should comfort you, because most of the stars are indeed solar metallicity and basically not alpha enhanced. And for example, if you project this out, this is a metallicity distribution that's not observed. So, but now we come to the fun part. What we have is, if you give me a star of a given metallicity and alpha enhancement, I can tell you it belongs to a population with scale height x. And now we can also say that same metallicity bin contributes that much to the surface mass density at the solar radius. So for each star, we get the scale height, and we get its surface density contribution. So we can just ask which fraction of all the stars in the column at the solar radius come from populations that have a scale height of h. So originally we anticipated, here we get some distribution for the thin disk, and then we get a bump out here, which is the thick disk. But that does not seem to be the case. There are comparable contributions to the stellar column density at the solar radius from stars that come from all kinds of scale heights. And indeed, if you want, right, it's not bimodal, and it's actually well fit by this straight line, which is e to the minus hz, which really looks like just some thermal distribution. So clearly a continuous distribution. Let me now return for a moment now back to the simulation. So the two things I've shown you is empirically, by taking this view of dissecting the galaxy into subsets of lifelong tags, basically chemical ages and abundances. Each component looks simple, and they form simple patterns. The oldest ones are essentially concentrated and thick, and the thinner ones, more radially extended ones, go further out. Let me now also, that you've hopefully gotten a little bit used to these funny-looking plots, do a little bit of a comparison in this language between the simulations and the data. So, again, what we're saying, these are the observations derived from SEGRE. If you pick half solar metallicity stars of slight alpha enhancements, that's their scale height, etc. So, and here is the same thing done by means of simulations. So, at first you should say, looks good. Until then suddenly, if you sit close enough that you can actually read the axis, first of all, the enrichment, which is one of the strengths of this model that's being kept track of, does not cover the full metallicity space. And secondly, red in the observations means a scale height of 1 kiloparsec, and in the models of 2 kiloparsecs. So this is why you see, in a qualitative sense, things fit well. In a quantitative sense, not yet. But simulations can be great sources of comfort nonetheless to observers, and I want to show you one example because I've been mumbling about, these alpha enhancement, these monoabundances. At a given metallicity and given alpha enhancement, stars kind of should have the same age. I didn't quite say it that way, but I implied it, right? The alpha enhanced ones are old, etc. Now, you can go into the simulations well, the whole messiness of enrichment in 3D is kept track of. And then you can ask, if I now go into my simulations, I pick all the stars that are 10th solar and have some alpha enhancement, or that are solar and have no alpha enhancement, and then I look up their true ages. And I ask, how much do those ages vary? What's the variance of the ages? And indeed, blue means less than a gigayear. Except for, so there's a, don't ask me about it now, because it's, I guess if you spend 20 minutes on it, it becomes an interesting story. If you spend 2 minutes on it, it's just a messy story. So for the most part of this abundance plane, abundances, at least in the simulation context, are actually 1 gigayear-ish or so, at least age rankers, right? You just want to sort them in age. The actual age is a somewhat separate story. So, but that, I won't delve too much into this, but I want to do two things. Not only summarize where it leaves us, but also talk a little about where this may take us. So the one thing I did try to hammer home, I also did in my house colloquium earlier this year, is that it's a useful way to sort stars first by their lifelong tags, which could be age or abundances, and then ask what the spatial distribution looks like. If you do that in the Milky Way, you pick stars of a given metallicity alpha enhancement. They are as simple as can be. They are isothermal in the vertical direction, exponential, single exponential, and in both directions. Now, their scale heights and scale lengths are very strongly correlated in a way that basically says, yeah, you see directly that there was inside-out growth in the Milky Way. And if we use that same trick that you measure the abundance of a star that tells you it belongs to a population of scale height x by 1, you count up the stars, you find that indeed the temperature distribution of the disk is, if anything, looks thermal but not bimodal. And there's a continuum of all of kinds of disk scale heights. I've shown you initial comparisons with the simulations, and they show this, same qualitative abundance or age-dependent patterns. And the nice thing is, if you have simulations to do enrichment, you can either look at the observable, the abundances, or you can cheat and look up the actual age. It happens. To the extent that this qualitative picture is correct, the continuous distribution of scale heights or temperatures and the simulations seem to imply that the present-day thickness or temperature of each component is in comparable portions a birth signature, because the gas hadn't settled quite that much, and a subsequent heating signature. So now I do have 5 minutes, right? 6, 4, whatever. Let me actually talk a little bit about where this should take us, because God willing, Gaia will be launched in less than a year. Is that still right? That's not only the party line. That's the party line believed by the practitioners. That's right. We now enter a brief phase when it's always 10 months from now. That's right. Let me just talk a little bit about what needs to be done or should be done in the next few years. Now, if you look at the golden dots there, those are the stars from Segway, whose analysis I just told you about. The advantage is they have a well-defined selection function. We can get very good photometric distances, etc. The drawback is they were largely taken as a consequence of an extragalactic survey. So wouldn't it be nice to actually look at the disk, not only out of the disk. And Apogee, Gaia, ESO, and a variety of other surveys are doing that. Because I've talked a lot about the vertical structure. I was a little more hedgy about the radial structure, and that's because if that's a sample distribution, it's hard to say something about the radial profile of the thin components. You may have noticed in the radial direction there were a lot of them that actually had huge error bars or even upper limits. Second thing, obviously, we need to go analyze orbits, not positions and velocities, because I declared that to be primitive. I want to just put in one interesting fact why that's a surprisingly, actually a very hard problem to do a dynamical model. What the bottom right figure shows is an illustration of how far you can see with Gaia before dust, crowding, or other things stop you. Now, if you want to get to the potential, I just do it as a scaling relation. The most primitive version is you can get a potential from a combination of, put this over here, a logarithmic gradient in your tracer density and the velocity dispersion. So that means, let's presume you either, because you don't understand your 3D dust at the 10% level, so you don't know whether your stars fall off because you haven't quite accounted for dust or because they really fall off 10% steeper. And instantly you have a 10% error in your potential to do things like figuring exactly out how much dark matter is near the sun. To figure out whether the halo has a core or not, you need to do 10% or better. The other reason is if, you have a billion stars, 1 over square root billion is a small shot noise error. So you'll be completely in the systematic analysis limit and indeed not knowing traces. Now let's presume you're slightly confused about the metallicities of your tracers. Now I've just shown you that depending on the metallicity, these things have very different spatial distributions. If you screw up sorting your stars exactly into the right metallicity bins, you can easily get a 10% error. So this is why there's an interesting part, both dynamical modeling and in our field of modeling the Milky Way. The way you deal with dust extinction, selection effects, all of this has to live up to the same level that the cosmological surveys have learned to do over 15 years. The point is, it will be great to get real ages for large sets of stars. Now, I sold you the abundances as a good age proxy, but I hope I was honest enough by saying, well, that's all we can do at the moment. It's not bad, but it's not perfect. And actually, I showed you this beautiful plot how as a function of age in the simulations, the scale height just thins out smoothly. If I do this as a function of abundance in the simulations, that's one of our skeletons. I have not shown you this plot. It looks uglier. So clearly, having the true age, alpha enhancement as the speed of enrichment, and metallicity as the degree of enrichment are three pieces of information that hopefully can tell you something about the feedback and enrichment simulations. And a very big task, it's actually shown a comparison with one simulation from Greg Sisson. It's actually very hard to run extensive sets. It works in some ways, but the disk is a factor of too thick in some ways. There are slight differences in the patterns, etc. So, which aspects of this? We see these beautiful patterns in the Milky Way. Which aspects of the disagreement are because we didn't quite have the right prehistory, or the feedback in the star formation and the enrichment recipe wasn't quite right, or which aspects of this, for example, radially exponential profiles, could just be generic features. So, but you need to run suites of simulations with somewhat different prehistories to see which of these disagreements are a consequence of dynamic prehistory, your simulation approach, and also ask the question of, are there generic features that come out? For example, one of the interesting things is with this radial migration business. You make the radial profile of stars exactly when they were born. It looks very bumpy because, stars are born in bumpy fashion. As you wait, the radial profile, as stuff gets stirred, of a single-age population asymptotically becomes an exponential. Who knows whether that turns out that radially exponential is just a consequence of many, many, resonant scatterings. So, I think I've shown you that even this 0th order idea, old stars are thick and centrally concentrated. Young stars are thinner and far more radially extended. Except for perhaps Andromeda, it is very hard to do this in anywhere near the detail that you can do it in the Milky Way. So I think the Milky Way does allow you, if you look at it that way, to do tests of how disk simulations work or not that you cannot do with any other galaxies. The exciting and slightly scary part is that I still feel that my statement is true and will be true now or in 5 years. None of us will have the tools to do justice to the full information content of the Gaia data. Thank you.
So thank you for a very interesting also perspective on the future. It means in about 5 years we're still going to be able to work on similar problems.
Well, you think you're the only ones here, right? With exoplanets, you first go for only more, then you go for smaller, then, we got our line going here.
Can I ask for questions from the students and postdocs first, and then we'll open it up for everybody? Anybody has a burning question? Or non-burning?
In case you're not a postdoc.
Separated from the story about correcting the observed sample from survey. From the observed sample to the intrinsic sample, and you completely separated that from modeling that corrected data set to get an extra model.
Yeah.
I'm sure they're actually connected to the implementation.
Okay, let me perhaps, this whole business came up twice indeed. The first statement was doing this correction, that just means this is all you need to do to figure out under which circumstances a G-dwarf ended up in your catalog. So then you get a perfect, that's all you need to do if you want to make, say, maps of G-dwarf number density, right? The other part that came here, what was that? Exactly, that ended up, this part here. That is a separate question of if you know I have all those G-dwarfs of a given abundance, for how much stellar mass do they stand? You have to both put in the IMF, and you actually also have to put in a model of the age distribution of those stars. So that's why you can do the first step and then only deal in number density space if you want to know what these stars stand for. As, in terms of stellar mass, then you'll have to do that second step. Let me actually, does it kind of go in the direction, was those the two things you were asking about? Okay, I guess imagine you want to get age distributions of stars with Gaia. So you'll go through. The best way to get ages is for stars that, are on the horizontal branch, because if you measure the parallax, the luminosity, you know the luminosity exactly, and if you know their metallicity, you know they you turn off the main sequence at the same luminosity, and so you get their age, because you know the main sequence time, lifetime at a given metallicity and luminosity. So you only get ages essentially for subgiant branch stars. Now, then, to get the true age distribution, you need to figure out exactly for which part of the subgiant branch you get how good an age. And this all varies, of course, as a function of distance, quite dramatically, the fraction of stars for which you get ages, etc. So there are many variants of, if you have, you get a Gaia catalog, all of things will have age entries. Some age entries are qualitatively useless. You may have an M dwarf, you say, it's probably younger than the age of the universe. That's about all you can say. And so how you go from such a catalog to a mass-weighted age distribution of stars in the galactic disk, that's an interesting thesis if you like math. It's actually interesting stuff how to work this out.
Do you have any other questions? Oh, no, you're not postdoc. Sorry.
Oh, he is, kind of.
Postdoc is fine. Go ahead.
So when I said that the scale heights are off by a factor of 2, that is not true. On average, the mass-weighted scale height is actually only 25-30% larger than actually observed. However, the simulations have a very thick, have a 2 kiloparsec old disk, or a rotating inner halo, rapidly rotating inner halo, etc., which seems to trace itself back to still a very turbulent early phase, stuff. Things just in the simulation were wilder at redshift 1.5 or 2 than they seem to have been in the Milky Way. But again, Greg has not, Greg should speak on this. Greg has not, run many different ones. I mean, the question of, remember, one of the reasons why he gets such a thin disk and not a more dramatic bulge compared to others is because he put in early stellar feedback. But that's just, he deposits the radiated energy of the stars that don't go supernova. Whether that recipe is quite right, that's not entirely clear. So I think running a suite of these things and see what matters is the only way to go about it. But as opposed to molecular clouds, cosmology is the great advantage, at least at a statistical level. You have an ensemble of very well-defined initial conditions, right?
So you saw us the Milky Way as being a very average galaxy. So that's towards Mars, but not its environment. So
Say again?
For its environment. So it turns out that the Milky Way doesn't live in a filament where it's a typical halo, sort of 10 to the 12 solar mass halo size lives, but it lives in a war, which is an unlikely place for such a large halo to be. So that would hint at a very quiescentism. Maybe at least quantitatively may explain this discrepancy there.
Yeah, I mean, perhaps you're just saying from a cosmological perspective what I said when I said the Milky Way is not average in being so disk-dominated for such a massive galaxy.
If you assume initial mass function for stars
Mm-hmm.
and enrichment and supernova, then you can convert your enrichment history to timescale.
Mm-hmm.
Timescale for the radio scales to change.
The answer is, I mean, the simulations are run by Greg, so the answer is I don't know. I'm happy to ask him. But I mean, the point is the overall, the metallicity distribution of the disk at the end comes out okay. It's just the alpha enhancement. There are too few dramatically alpha enhanced stars. That's the biggest discrepancy.
We have at the moment some ongoing spectroscopic surveys like Apogee and ISO Gaia-ISO. Now, for making full use of the Gaia kinetic data, there will be also some chemical information available from Gaia. Will this be sufficient for you to distill the full information out of the Gaia data, or would you like to have additionally ground-based spectroscopic follow-up?
So, let's see. Are any? No, I can speak freely about Gaia abundances, I suppose. No, I mean it's true that Gaia will get some abundance information from very low dispersion spectra, but so the abundances come in many ways. If it's just metallicity is a good number to have because even to get ages, you need to get the metallicity, etc. So that's a number which I think even low dispersion information would suffice. What's not clear to me, just because I haven't thought it through, ISO Gaia will get beautiful abundances for twiddle 100,000 stars out of, a billion. Whether, it's underappreciated. The worst source of noise in all of this is sampling noise, right? Because you want to get a gorgeous spectrum of 100,000 stars to get detailed abundances. You have no time left to look at the other stars, so you know nothing about the abundances. And if you care about the stars, then that's the right thing to do. If you care about the abundance distributions in the Milky Way, it's not obvious that that's the right thing to do, at least. So I think there's a lot of work that needs to be done to tie in the resolution 30,000 spectroscopy to the resolution 5,000 and 2,000 and resolution 80 spectroscopy. And it's not clear to me that, I think until this actually happened in the Gaia age, it'll be 2019 or 20 until we have good cross-calibrated catalogs.
Let me make sure that I understand. When you take alpha to ion as a level of age, you have to assume that at a given time, this ratio doesn't scatter very much within an age.
Yep.
A related question is, when a star is born in a certain, let's say, subpopulation characterized by the scale heights, it will stay in that subpopulation for the rest of its life.
Yes, because I defined the subpopulation by its abundance. So to the extent that the star never changes its...
Well, this is the first. The second part will be scale heights.
Okay, so let me perhaps to here. So if I... The definition of subsamples is time invariant because I assume once stars are born, these numbers don't change. I would presume that for each of them, their scale height, of course, if we had lived at redshift 0.5 and had played the same analysis, all scale heights would have been lower, right, because there's subsequent heating. And the question of how to interpret this as age, so I think real ages are key to get. Fact remains, if I just separate them by these two observational proxies, subpopulations split themselves up into a sequence of beautifully isothermal single scale height distribution. So that's, I can be a strict empiricist and say, I split it by something that has nothing to do with the spatial distribution or the kinematics, and this is what comes out. So that's a pattern that somebody ought to explain.
And Eva has the last question. And anybody else, please just come down and ask them about that so that I get
Okay. Let me repeat the question. The question was, what does any of the stuff that I showed here tell you how efficient radial migration is? The answer is that's the first answer is that's a hard thing to draw distinct conclusions. The one thing I can say, radial migration is a swapping of places. So if you're a centrally concentrated population and you look at it out here, you're most likely to find somebody who moved out, right? So that's a consequence of radial migration, is that a star that comes from a centrally concentrated population is most likely someone that has come from the inside. So what happens as you migrate outward, because the restoring force of the disk decreases, as you migrate outward, you feel very happy because the same kind of, the vertical action or vertical kinetic energy allows you to become thicker. So if radial migration plays a role, the prediction is that indeed thick components have to be centrally concentrated. But if I look at the simulations, right, there's this mix of stuff that happens at birth because the gas isn't completely settled and stuff that happens afterwards. So whether we can ever sort this out, and I should mention there's a project named Hermes, which says we get good enough abundances that I know which two stars were born in the same cluster. If you then find them at radii a kiloparsec apart, you know they must have migrated. The drawback of Hermes is that you will look at 100,000 stars, you're likely to find one set of triplets, two sets of twins, and everybody else has come from a single family. So this is why this test is actually not very, very stringent either.
So my second question
Yep.
is, you said that you determined ages for subgiants, and so in answer to another question, I was just wondering, how do you separate the subgiants from dwarfs?
I'm sorry. With Gaia, we should be able to. We need Gaia to get useful ages from subgiants, right? So, and there it's simply a matter of you measure the luminosity, you measure it, right? Now, I have not determined for any, whenever I talked about ages, it was the simulations, because that's all I'm stuck with at the moment, right? It would be nice to have actual ages.